Welcome to lesson 22, optimization. So you might remember in lesson 16, when we learned about maximum and minimum values, we sort of talked about, or we at least mentioned, that some of the most important applications in calculus are what we call optimization problems, where we want to find the optimal or best way of doing something. So examples could be what shape of a can will minimize manufacturing costs, any kinds of minimizing materials and costs for businesses, um, or even like safety issues like what angle should a freeway off ramp be inclined to minimize tires slipping. So there's all kinds of different engineering feats, from civil engineering to manufacturing or mechanical engineering, that would all require finding answers to these types of questions. And so what we're really doing to find those answers is to find a minimum or a maximum value of a function. So if we have a function that tells us the cost, then we want to find the cost to produce something, let's say. Then if we find the minimum of that function, then we have found a real world application of using first derivatives. So what we're going to do in this lesson is basically that type of problem where we're going to be finding minimums and maximums as they apply to the real world. So we'll start with an example and we'll kind of walk through a process of doing one of these. And then we'll look at guidelines, sort of steps that you can follow in order to solve any optimization problem. So we'll start with, what are the dimensions of an aluminum can that holds 40 cubic inches of juice and that uses the least material? So we have some constraints here. We know that there are 40 inches cubed of juice, which is a volume. Whoops. A volume, right? Inches cubed. That's the volume, and it's a set volume. It's not going to change. But we do want it to use the least material. So the thing we're trying to minimize here, right, the material used for the can. And we're supposed to assume that the can is cylindrical, and yes, it's capped at both ends, otherwise it would not actually hold the juice. So here's a cylinder that we can kind of use to help us visualize. And if we're trying to minimize the material used, what does that mean geometrically that we're trying to minimize? It's not the volume. Volume is set. The material used, what geometric thing represents the material used? It would be the surface area, right? Which is the surface area. That's the amount of material that's used. I'm sure it has a certain width, but still the idea is to minimize the surface area of this can. So you may not remember the equation for surface area, but that is the next thing that we need to come up with. We need an equation, because if we're trying to minimize something, we need an equation for it first, and then we can take a derivative, find critical numbers, and hopefully find a minimum. So in terms of surface area, if we're looking at a cylinder, right, that has a particular height and a particular radius, the surface area will first be the areas of the two bases, which is the two circles. So 2 pi r squared will give us the area of the top and the bottom. And then the lateral surface area is what we call this area around the outside of the cylinder. That is the circumference, 2 pi r times the height. Now, don't worry that you would have to be able to come up with something like that on your own. I will give you geometric formulas on assessment problems, but that is, in fact, just what our surface area is going to be in this situation. So we want to take a derivative, right? And we want to figure out the critical numbers, but you might notice that we have a problem. So right now, this equation has both an r and an h in terms of input. So which variable do I take the derivative with respect to? I really only want one input variable. So is there some other fact that we know in this problem that could allow us to maybe use a secondary equation to get rid of one of these variables? Remember this set volume over here? So we know that the volume of a cylinder is pi r squared h, okay, or maybe you didn't know that, but it is. And that in this problem is set at 40. It's not changing. The aluminum can is going to have that volume. So maybe I think it would be a little harder for me to solve that for r with the square root. So maybe I'll solve it for h. And then I'm going to substitute that in over here so that my surface area function only has r in it. Now, it's always a good idea to simplify as much as possible before you go ahead and take a derivative. So it looks like the pi's will cancel, the r will cancel with one other r in the denominator. So I'll have just 80 over r. So my surface area is equal to this equation. And since I'm trying to minimize it, I'm going to take a derivative. So with respect to r would be 4 pi r minus 80 over r squared, or r to the negative 2. And then I want to set that equal to 0. And so in order to do that, it might be better for me to actually rewrite it as one fraction. So in other words, I'm just going to multiply this one here by r squared over r squared so that I can actually rewrite this with one numerator and one denominator. That will then allow me to set this equal to 0 and solve. So it looks like I have r cubed will be 80 over 4 pi, which is 20 over pi. And so if I cube root that, r will be the cube root of 20 over pi, which I can get a decimal approximation for. It's about 1.85. So that would be when this derivative equals 0. Of course, it would be undefined at r equals 0. But it doesn't make a whole lot of sense for us to be talking about a can with a radius of 0. So we will just look at the r equals 1.85 as a critical number. And then if I was going to just do a quick sign chart, I'm going to cap that sign chart at 0 because obviously the radius isn't going to be less than that. And if I plug in something less than that into, obviously this will be positive, so probably just into this numerator, something like 1, and at 4 pi minus 80, well, that is definitely negative. And if I plug in something bigger like 10, I have 4 pi times 1,000 minus 80, so that's definitely positive. So this surface area function is in fact decreasing until it hits this r equals 1.85, and then it's increasing, which makes the radius of 1.85 inches a minimum. So that helps me answer my question. It asked me for the dimensions of the can that would minimize the area or the material used. So I have an R of 1.85 inches. And if I were to just plug that back in, where is it? Oh, over here. H equals 40 over pi r squared. That gives me an H of approximately 3.72 inches. And so there are my dimensions of the can with the minimum amount of material. So let's just briefly take a look at what we did and kind of use that as a way to create a strategy for approaching any optimization problem. So first and foremost, just like with related rates and any kind of word problems you have to understand the problem. These aren't places where you can just mimic things. You need to read the problem a few times, draw a picture, actually assign variables, figure out what's a constant. You have to break things down. If you don't do this step, you're sort of shooting yourself in the foot to actually being successful. So then the next step, and this is really the critical step here, is write the equation that models the quantity to be optimized. So you want to start with the quantity that you're trying to maximize or minimize. That is your primary equation. Okay, this is your primary equation, the one that you're going to be taking the derivative of, because taking the first derivative tells us about maximums and minimums. So we want to start with the thing we're trying to maximize or minimize. Okay. Well, I guess I said primary right there, didn't I? Probably. All right, now often what happens is when you do that, like in our CAN problem, you have too many input variables. You've got an R and an H, a length and a width, something to that extent. So the next thing you need to do, if you have more than one input variable, is create additional equations. And those are going to come from how the elements of the problem are related, like you have a set volume, or perhaps you have a set footage or square area or something that you're using. You would write that secondary equation. That's not the one you're going to take the derivative of, but you're going to use that to eliminate everything except for one input variable, just like we did in the CAN example. We solved for H and subbed that in. So that's what those extra equations are. Once you've done that and you've subbed it into your primary function, you have only one input variable, then you're going to do your derivative and find your max and your min. So differentiate, find the critical numbers, use the first derivative test. Now, there's one important point I do want to make sure we touch on here, is that remember when we did the closed interval method and we took the derivative and we found critical numbers, but then we actually had to test the two endpoints and the critical numbers to figure out which one was the highest or the lowest, depending on finding a max or a min. You may have an optimization problem where there are actually endpoints that you need to test. So as you go through these problems, you always want to ask yourself, what are sort of my endpoint values for the input variable? And are these actually viable options? So for example, certainly we discussed in this problem that R is not going to be less than 0, right? So I have an endpoint right here. But is R equal to 0 actually a viable option? Could it actually produce a CAN? And it cannot. So we used that endpoint, but we didn't have to plug it in to make sure that it wasn't the max or the min, because it's clearly not. So as we go through these problems and I describe and work through some examples, I will be constantly talking about what are the endpoints of my input variable and do they make sense to test as an actual option.